In today's lesson, we're going to discuss continuity and one-sided limits. We're going to look at all of the different types of continuity, which include continuous at a point, continuity over an open interval, continuity on a closed interval, functions that are everywhere continuous. We're also going to look at properties of continuity and be able to use them to evaluate our functions. And we're going to learn about the intermediate value theorem and what it is able to tell us about our functions. The first type of continuity we would like to discuss is continuity at a point. If a function is continuous at a point, it means that I have plugged that value of x into my function and have been able to calculate a y value to partner with it. I verify this by taking the limit of my function as x approaches that particular value, which we're going to call c. When the limit is equal to the value of the function using c as my x value, then we say that the function is continuous at that point. The second type of continuity we're looking at is open interval continuity. Remember, when we use parentheses to describe an interval, it means that the boundaries are not included. So if I look at the graph of an open interval, whether or not my endpoints have actual y values on the graph is irrelevant, because I'm not looking at them as part of my interval. I'm looking at them simply as the boundaries. And I'm testing everywhere in between that all of the x values between my endpoints a and b have a valid partner of y on the function, and that the function creates a nice, smooth, continuous curve. Our third type of continuity is continuity over a closed interval. Now you'll remember, in a closed interval, your endpoints are included, and so they are also important. So we're looking at all of the things that we looked at in open interval. We're checking all of the values in between a and b and making sure that every x value has a partner of y. But in addition, we are also looking at what our boundaries are doing. So since a is my left boundary, I'm going to take the limit of my function as x approaches a coming from the right. If this limit is equal to the value of the function at a, then my left-sided limit exists. Now, if I look at the limit as x approaches b from the left, I'm now looking at the right side of my interval. And I want to know that my limit of my function as x approaches b is actually equal to the function value when x is b. If this is true, then my right-hand boundary limit exists as well. Therefore, if these both come true, then we have continuity over our closed interval. The final type of continuity we'd like to discuss is a function that is everywhere continuous. What that means is that no matter where I look on the graph from negative infinity to positive infinity, my function just happily carries along, having a value of y for every value of x. Some examples of everywhere continuous functions would be polynomials, sine of x, and cosine of x. Now let's discuss what might happen to a graph that would cause it to be discontinuous. The first one we want to discuss are holes. You're familiar with how holes are created. When we have a rational equation and we factor out something in our denominator and are able to cancel it, then a hole is developed. At that point, we know that that's a discontinuity, a break in our graph, somewhere where the value of x that we call c does not exist. However, we can make a piecewise function and define this exact point and give it a value, therefore plugging it in. And when we do that, we've removed the discontinuity. So holes are a removable discontinuity. Now, another type of discontinuity that's very similar to the one we just discussed is also a hole. This one is where the function is actually defined for the value of c where the hole occurs, but there's a different y value that is equal to that value of c. So it's a point that's somewhere vertically along where the hole is at, but not inside the hole itself. But again, we can fix this type of discontinuity and redefine the function, and therefore holes of any type are removable discontinuities. Now, the third type of discontinuity is called gaps or jumps. If I'm looking at a graph and my function from the left approaches a particular y value for my value of c, and then at a different point has a different y value, I'm looking at two different limits. My limit from the left is equal to a different y value than my limit as x approaches c from the right. Therefore, since my left-sided limit does not equal my right-sided limit, then my limit as x approaches c is d and e, and this is a non-removable discontinuity. Finally, we want to talk about asymptotes. When we have a rational function where we cannot cancel what causes our denominator to go to 0, then we have an asymptote that shows up. So if I have a function that has a vertical asymptote, it's not just a regular discontinuity. What I'm looking at is something that causes my function to actually approach something I can describe. If I look at the limit as x approaches my value of c from the left, my function shoots off to negative infinity. If I look at my limit as x approaches c from the right, it shoots off to positive infinity. These are both things that I can describe. However, they are also discontinuities. So we simply call this is an infinite discontinuity. So now let's talk about what really defines continuity. How do we look at a function and know that it's continuous? Well, we have a little checklist. The first thing that we look at is that we want our f of c to be defined. That means I want my value of x to be able to be plugged into my function and to receive a y value. Secondly, I want to be able to find the limit of my function as x approaches c. I want to be able to evaluate my limit. And finally, if my limit as x approaches c is equal to the actual value that I found when I plug that c in, then I can definitely say that my function is continuous. So how do we know if a limit exists? We have a theorem. It's called the existence of a limit. If my limit as x approaches c from the left is equal to a value of L, and my limit as x approaches c from the right is also equal to this same value of L, then my limit exists and my function is continuous. So we've already discussed the things that can cause a function to lose its continuity. But let's talk about the things that don't hurt it at all. All of the things that we do to functions, multiplying by a constant multiple, adding functions, subtracting functions, multiplying functions, dividing functions, even function composition. If our functions are continuous, then any of these operations can be performed and our functions will remain continuous at that value of c. The key to continuity is knowing your domain of your function. You've got to look at your functions and understand what you know about them. So when we look at polynomials, we know that polynomials are perfect everywhere. That means that polynomials are continuous from negative infinity to positive infinity. They're continuous everywhere. Exponential functions, also, there's no values of x that we eliminate from our domain. Therefore, exponential functions are continuous everywhere. Some of our trigonometric functions are continuous everywhere. For example, sine and cosine. However, cotangent, tangent, and secant and cosecant, all of those have asymptotes. And so there are areas in those functions that have infinite discontinuities. Rational functions. Anything that causes my denominator to go to 0 is going to cause a discontinuity in my function. Radical functions. Remember, we have to limit our domain to keep our imaginary numbers from showing up. So anything that's eliminated from our domain is considered a discontinuity in our function. Logarithms have a vertical asymptote that bound them. There are only certain values that we allow inside of a log. Remember, no negative values inside a log, no zeros in a log. Therefore, we have limitations, and we're going to have discontinuities in our function. So when we look at functions that have discontinuities, we don't want to just ignore them. We're going to look at them in the form of a one-sided limit. So let's take a look at some of our domains. For example, if I have the function f of x equals root x, I get a domain of 0 to infinity. That means that if I take a one-sided limit, the limit as x approaches 0 from the right, now I can't take it from the left because it doesn't exist on the left of 0, but if I come towards 0 from the right, then that limit is going to exist, and I'm going to get the same value of f of 0. And therefore, the right-sided limit exists for this particular function. Let's look at one more. We have f of x is equal to root 5 minus x. It has a domain of negative infinity to 5. If I look at 5 coming from the right, my function does not exist. It's discontinuous. However, if I do a one-sided limit, the limit of my function f of x as x approaches 5 from the left, then I'm going to get a value that matches f of 5. And therefore, the one-sided limit coming from the left exists for this particular function. In our first example, we want to find the value of c that will make this function continuous. It's a piecewise function made of a quadratic and a linear equation. The quadratic is not allowed to have the value of 5 in its domain. It takes all of the values from negative infinity up to 5, but not including 5. Now, the linear equation, although it can use 5, it needs to be able to graph right where the hole occurs. If for any reason the linear equation has a different value of y where x is 5 than the quadratic would at that same point, then we'll end up with something that looks like this, like a jump. That's a non-removable discontinuity. So what we want to see happen is the quadratic graph, it has its little hole at 5, and the linear equation fills the hole and then takes off and continues to positive infinity. That would make our function continuous. So, if the function is going to be continuous, then the two functions need to be equivalent at that point. So we're going to set them equal. Now, our x value at that point is 5, so we're going to let x be 5. Even though the quadratic can't use 5, it's okay because when we remove 5 from the quadratic's domain, the hole appears at exactly the right place. So, we have 25 minus c is equal to 20 plus 2c. And solving for c, we subtract the 20, we add the c, and I get 5 is equal to 3c. C is equal to 5/3. So my equation x squared minus 5/3 for all values of x that are less than 5, and 4x plus 2 times 5/3, which is 10/3, for all values of x that are greater than or equal to 5. And we've made our function continuous so that it would graph in this manner. You have a problem very similar to the one I just did. So send me just the values that you find for C, and then I want your work shown to me tomorrow morning when you come to class. The intermediate value theorem describes the relationship of a continuous function. If my function is continuous on a closed interval, remember that means that the values of my endpoints are included. So if I have an endpoint A, then I must have an f of A in my function. And likewise, if I have an endpoint B, then I must have an f of B in my function. And if the function is continuous, then all values of x between A and B will provide me with a corresponding y value, making a continuous smooth curve between the values of A and B. Now, if I pick a random y value and I call it k, and I find that value on my function, there must be a value c within my interval in which f of c will give me that value of y called k. So it's important to understand what the intermediate value theorem can do and what it can't. The intermediate value theorem is simply an existence theorem. It says that if I have a function and it has to pass between two numbers, then it has to hit all of the values in between those two numbers. So let me explain this again in another way. If I have a function on a closed interval from A to B, and f of A is 7, and f of B is 1. If the function is continuous, then it hits all the values between 1 and 7. So any number that I pick in between, any value of k that is between 1 and 7, there must be an x value within the interval that will provide me with that y value. The intermediate value theorem cannot help us find this value. It can simply tell us that it exists. It's an existence theorem. In this example, we're asked to use the intermediate value theorem to find an interval of length 1 which contains a root of f of x equals x squared minus 4x minus 5. So what I'm looking for is a change of signs in my function, because if I have an f of x value that's negative, and then a distance away I have an f of x value that is now positive, then somewhere in between my function must have passed through 0 to change from positive to negative or from negative to positive. So looking at my function that I have, it's a polynomial. Well, polynomials are continuous everywhere. There are perfect functions. So I'm going to start with something easy, my f of 0, because that's my y-intercept. I can already see it. When I plug 0 in, I'm going to get negative 5. So I just need to find a value that's going to give me a positive answer. And this will begin my search for my interval. I just need to make sure that it's only 1 unit away from 0, or from my boundaries, that I create one that is 1 unit away from each other. So I'm going to choose the value of -2, and I'm going to plug that in and see what happens. So plugging in -2, when I square -2, I get 4. When I multiply -4 by -2, I get 8, and then I'm going to subtract 5. So 4 plus 8 is 12. 12 minus 5 is 7. That's a positive value. So that I know that at this moment I have an interval from -2 to 0, and somewhere in here there's a root, because it wouldn't change from positive to negative without passing through 0. So I'm going to come in a unit, a half a unit, because I just want to get a unit in between, a space. So if I cut my interval down and I'm going to check it, and I say, okay, I'm going to take -3/2. That's -1.5. And then I'm going to bring my 0 in to the left at a -0.5. And then I'm going to check it. So if I take f of -3/2, and I do the math, common denominators, I get a positive 13/4. Now checking my other endpoint, my f of -1/2, and I make my common denominators. I get positive 9, -20. F of -1/2 gives me a -11/4. So my two endpoints, my A and my B, from -3/2 to -1/2, it's 1 unit apart, and somewhere in here, in this 1 unit, there is a root of my function. And so my final answer is the interval that I came up with. It's important to notice, though, the intermediate value theorem didn't help me find my root. It simply guaranteed that I would find my root. Now in this example, I'm asked to use my intermediate value theorem to show that my function of x, x cubed plus x, takes on the value of 9 for some x in the interval from 1 to 2. So what they're saying is that somewhere in this interval, there's an f of c that is equal to 9, and I just have to prove it. So I find f of 1, and I get 2. And I find f of 2, and I get 10. If I have a function where f of 1 is 2 and f of 2 is 10, and my function is continuous, which I know it is because it's a polynomial, then I'm guaranteed that somewhere in between, there's an x value we call c that's going to give me my f of c equals 9. And so my work that I showed using my endpoints proves that somewhere on f of x between the boundaries of 1 and 2 that there is a value of x that will give me an f of x value of 9. And once again, my IVT did not tell me how to find this. It simply guaranteed that I would. So we show our work and we say, therefore, by the intermediate value theorem, there exists an f of c that equals 9 in the interval 1 to 2 of the function x cubed plus x. So now, 2 more questions for you to try, very similar to the examples that I've already given you. So make sure you take a look. If you need to, go back and rewatch the examples that I did. All of your Google answers have to be in my Google account by 6:30 in the morning, and make sure that you have your work to prove to me what you did to find your answers when I see you in class tomorrow. Okay, so this is going to be our opening discussion for class tomorrow. So make sure you write down all the information and follow my instructions. I'll be checking your work in the morning, and then we're going to discuss our thoughts and ideas about this concept. And the final thing for you to write down is all of this homework. Don't worry, I'll be around to help you, and you can ask me questions anytime you need to. See you tomorrow.